propose that we thank Christophe again, and that we move to the last talk of the session by Bhupal Dev that will tell us about anomalies, right? Interpretation of those anomalies.
Hi, can you see my screen?
Yeah.
Sorry.
Full mode, full screen, perfect, okay. Good,
Okay,
so please.
So yeah, I would like to thank the organizers for this very nice meeting, and look forward to it every year. So I'm very happy to give a talk on the anomalies. I was asked to kind of give an overview of the current anomalies and the implications for BSM physics in particular. So let me just first make some general remarks before I go into the details of the particular anomalies I'll be talking about. So this is an era of anomalies. There's a growing list of anomalies that we have the discrepancy between the experimental measurements versus the theoretical predictions coming from the standard model. However, we have to take this with a grain of salt. There are many people who are kind of very skeptical about these anomalies, and they're rightly so, because in the past, most of the anomalies have just gone away. And this could be due to many reasons. The anomalies could disappear due to, for example, statistical fluctuations in the data. And the most famous example from recent past we have of that is the 750 GB diphoton excess, which was seen in both CMS and Atlas in late 2015, I believe. And then with more data, it simply disappeared the year after. Also, the anomalies could be due to some systematic effects or some background uncertainties that were not accounted for in the data set before. And most recent example of that, I would say, is the Koto anomaly. So Koto is this experiment at JPark, which measures the K long going to pi naught nu bar. And they had seen some excess with respect to the standard model prediction in 2019. But then last year, with more data, they found that the background was underestimated. And once you take into account that the actual background, then there is no discrepancy anymore with the theoretical prediction. Or there could be other simpler reasons, like, for example, it could be just an experimental error. Like, for instance, we had the superluminal neutrinos from Opera experiment about 10 years ago, but it just turned out to be some loose cable. Or there could be some more complicated unknown issues. For instance, this DAMA experiment has been seeing this annual modulation signal for a long time. Now it's almost at 13 sigma. So nobody really doubts that there is something there, but I guess nobody knows what exactly is going on there. Most likely it's not a signal of dark matter, it's something else. Or there could be just this very exciting possibility that the anomaly could be some genuine new physics signal, and that's what we'll be most excited about. There is no dearth of new physics ideas out there. There are hundreds and literal hundreds of different models that one could have, and then you could just play around with that and see which new physics model could fit the anomaly out there. In general, I would say it's the anomalies are a good driver of scientific creativity, both for theorists and for experimentalists. On the theoretical side, as I said, you have so many of these models, and then you could try, which model can fit the anomaly better. And then, just instead of playing around with your own favorite model, you should have an open mind and see which one is really preferred by the data. And from the experimental side, again, so it's a good opportunity to understand all the different parts of the experiment, the systematics, the backgrounds, and all the detailed instrumental effects and so on. So it's not just ambulance staging or just getting some citations. Rather, we should take it as a good driver of scientific creativity. Okay, so with that, let me just give you a list of existing anomalies. I do not claim this is an exhaustive list. There could be some anomalies which I missed, and if that's so, then please let me know, and I would put it in the list. We also try to so we have just started recently creating a repository, online repository on GitHub to just list all these anomalies and their possible explanations. So again, this is a huge field. A lot of people are working on this. So by no means we can just do it by ourselves. We invite community involvement on this in maintaining and updating this repository. That's why we moved to GitHub, so everybody can really contribute there. So please feel free to contribute there and edit this GitHub page and add your favorite solutions or your favorite anomalies there if it's not already listed. So again, I don't have time to go over all these different anomalies. Also, I'm not an expert in all of this. So I would just have some I have some personal bias, and I will just discuss few of them in the remaining time. But I should just point out to you that many of these anomalies have been already discussed in this meeting or will be discussed today and tomorrow. For instance, these anomalies in the LHC data, these multi-lepton anomalies, there will be a parallel talk by Bruce Melato, who will talk about this and some recent updates as well. Similarly, for the muon G-2, we just heard the excellent plenary talk by James Mott, and there's a mini review talk by Hartmut Wittig this afternoon. And also there are many parallel talks, on different BSM interpretations of this G-2 anomaly. About the B anomalies, we just heard the talk by Christoph, and there will be also many parallel talks which cover some of the BSM interpretations of these B anomalies. There is also neutrino parallel talk on this LSND mini-boon anomaly, which has now gone up to about 6 sigma. So this is very interesting. There are also some talks on the xenon wonton axis. Recent, I think there was a plenary. Yeah, so in the plenary talk yesterday by Nat Mora, he explained this in some details, and also there are some parallel talks in the dark matter section session. So if you're interested, please go look at that. About this 511 kV gamma ray axis, there is a parallel talk. So I should I should mention here that this is about 58 sigma axis now. So there's no doubt that there is something going on there, but just that it's astrophysics is quite messy or there near the galactic center. So we really can't say, can't claim that we have some new physics or some dark matter out there. So yeah, this is one general comment I would put here. So compared to the HEP side versus the astro side. So on the astro side, you can have much more than 5 sigma, but still you cannot really say with 100% confidence that you have seen some new physics out there, because there are just a lot more astrophysical uncertainties that could play a role there. So we should just keep that in mind. And also about this cosmological tensions like the Hubble tension and the sigmite or the SI tension. There was this was covered in the plenary talk with Elizabeth. And also there are some parallel talks that you can listen to. And finally, about this nanograph, the detection of the stochastic gravitational wave background, there is this excellent talk yesterday by Mora. So please look at that. Okay, with that, so let me just give the brief outline of the remaining part of my talk. So I'll mostly focus on 3 main anomalies here. 2 of them are relating to the B anomalies, both in the charge current and the neutral current sector. So I'll mostly focus on a common new physics explanation for this and complementary high PT LHC tests on that. And this is related to Christoph's question in the last talk, that is there any kind of direct test of these anomalies at the LHC. And then the second part of my talk will be about the muon G-2 anomaly. And so I'll, again, I won't repeat all the things that have been already said, but I'll try to connect it to the B anomalies, because both of these could be, could give us the hints of this Lepton-Favor universality violation. So whatever new physics is there is the underlying new physics. So you could have, in principle, you could explain both the B anomalies and the muon G-2 anomaly with the same new physics. And also I'll talk about some tests at the LHC and future colliders. And in the last part of my talk, I'll briefly mention the possible connection to neutrino mass. Okay, so let me just start with this muon G-2 anomaly. So this we just heard in this session. So there is this now 4.2 sigma discrepancy with respect to the standard model. And of course, this is not the end of the story. There is this theoretical uncertainty that comes into picture here. In particular, this BMW result is not totally compatible with other theoretical predictions, and this is much closer to the experimental value. So this, eventually it could be that this is not some new physics, but it's just everything is fine, consistent with the standard model. But I would like to make two comments in this regard. The first thing is that if indeed whatever this BMW collaboration is claiming, if this change in the hadronic vacuum polarization is closer to the experimental value, then of course the muon G-2 anomaly is no longer there, but the problem just shifts to a different sector. So the problems might arise in the global electroprecision field, and this was pointed out in this nice paper last year. soon after the BMW result. So basically the same contribution, the hydrogen vacuum polarization contribution appears in the RG running of the fine structure constant at higher loops. So, and it will lead to some problems in the global electrode precision fit. So this is something that one has to keep in mind. And maybe related or maybe not, there is some unresolved issue in the electron G-2 sector as well. In 2018, there is this measurement of the fine structure constant using cesium, and using that and comparing that to the standard model prediction for the electron G-2, there is this 2.4 sigma discrepancy that was pointed out. And this was in the opposite direction because for muon, the experimental value is larger than the standard model prediction, whereas for the electron case, it was found to be smaller. However, recently there is a new measurement of the fine structure constant using rubidium, and they do not see the same effect. They, in fact, now have just a 1.6 sigma discrepancy with respect to the standard model, and also this is now in the positive direction, the opposite to what the cesium result was. So again, so this is something I think this is something interesting out there, because the cesium and the rubidium results are off from each other by more than 5 sigma. So at least one of the measurements is probably not right, or either or both of them. We don't know. In any case, we'll have more updates soon, I hope, and the situation will become clearer. So for the new physics solutions to muon G-2, so again, as James mentioned, there have been this anomaly has been out there for the last 20 years, and many papers have been written on this. So in fact, if you just take the last paper of this, the final result of the Brookhaven collaboration, then you get you get almost like more than 2,000 citations there. So I can't really cover all the different solutions out there, and also very recent result has also got almost more than 120 citations. Let me just make just a very kind of very general arguments on the possible new physics solutions. So you have this new particle loop. Some new particle goes into this loop, contributing to the muon G-2. So if you just do very rough in the back of the envelope kind of calculation, so you find that the new contribution to the muon G-2, it roughly goes as this new coupling square divided by 16 pi square, because you have this one loop. And then you have a muon mass square in the numerator, because you need to have chirality flip in order to get this get the magnetic moment, and then divided by some new particle mass square. Okay, so this is a very again very rough estimate. And it turns out that if you want to explain the discrepancy with respect to the experimental discrepancy with respect to the standard model, then the size of this new contribution has to be of the order of the electroweak contribution to the G-2. So this you can achieve if you make either this coupling the same as the weak coupling strength, or and the mass same as the W boson mass, okay, the weak scale mass. So this gives you roughly the scale of the new physics that you would expect. So essentially, there are two choices. Since we have not seen any new particle at the weak scale with a weak coupling, so we have basically two corners of parameter space to look at this. The first one would be if you have some super weak interaction. This G is very small compared to the weak coupling, and then you need to have a small mass. And there are several examples of these, like axion-like particles, dark photons, some light G primes, and so on. So they fall into this category. The second choice would be to have stronger interactions. By stronger, I mean compared to the weak coupling, roughly the same scale as, or like if you have order 1 couplings, then you need to have some large mass in the denominator here in order to explain this the G-2 anomaly. And again, there are several examples of new physics out there. You can have new contributions coming from Tooth tablet models, from supersymmetry, from leptoquarks, and so on. So they fall into the second category. In any case, so whatever new particle you have in this loop, so essentially it can be anything. It can be a neutral particle, it can be charged particle, you can have scalar, fermion, case bosons, and so on. So you can see this nice review where they list all the different particles and their contributions to G-2. You can just systematically study all of them. However, you need to be very careful about the sign of the BSM contribution, because depending on what particle goes inside the loop, the sign can be positive or negative, but as I mentioned in the previous slide, so we need to have a positive contribution in order to explain the G-minus anomaly. So that one has to take care of. Now, for instance, if you have like if you have a doubly charged particle, I believe, then you'll get negative contribution. So we can't have that to explain this. And also we need to have a flavor non-universal coupling. This is mostly in order to avoid other experimental constraints because there are several experimental constraints coming from the electron sector and coming from the muon sector and tau sector, and also in principle coming from the quark sector. So you need to have some flavor non-universal coupling in general in order to avoid most of this constraint and still explain the G-minus anomaly. Let me just give you an example of that. If you look at the vanilla B-SL model, this is just a light G prime scenario. So you find that so the region which is preferred by the G-minus anomaly, which is shown here by this band. So this is excluded by other experimental constraints. Okay, so there's a lot of these beam dump experiments and neutrino scatterings and so on, and so all these experiments have already ruled out the B-SL explanation of this muon G-minus anomaly. However, now if you have a L mu minus L tau, so this is an anomaly-free combination. So you can have a a new gauge boson which is charged in this L mu minus L tau, and then you can have some room here still allowed by all the current constraints, and this should be you should be able to probe this in the near future. Okay, so this is just an example. Okay, so now let me move on to the B physics anomalies. First, I'll talk about the charge current anomaly. So this is usually parameterized in terms of this ratio of the branching ratios, B going to D tau nu versus B going to D L nu, where L could be the electron or muon, or you can also have the D star, where D star is just the excited state. So this process happens in the standard model. This is a flavor changing charge current process, and this happens at the tree level. Is only suppressed by the CKM. Here in this case is suppressed just by VCB. If you look at all the experimental measurements on this, so there's a very interesting trend that you can observe there. So so I have listed here in this table 11 experimental measurements to date from Babar, Bell, and LHCb for RD, RD star, and also there is one in the R JEPSI where you just replace the D with the JEPSI. So you can see that all these different measurements, they have different tagging methods for the other B, they have different tau decay modes and so on. They've looked at all of this, but in all these experimental measurements, the central value is consistently above the standard model prediction. So again, so this could be some huge coincidence, we don't know, but this is something that I find very interesting, okay, to notice. So here, if you combine all of these different experimental results, then you have this 1 sigma, 2 sigma, and 3 sigma. This is these are the preferred regions, and this is the standard model prediction. So if you combine all of that, this is I think 3.3 sigma, 3.4 sigma way. You can take this ratio RD over RD standard model or RD star over RD star standard model, and to first order, they're roughly equal, and they're pointing towards a 15% deviation coming from the standard model. So whatever new physics you have, that should be able to explain this discrepancy. So I'd like to mention 2 things here. So first of all, this is only seen in the BD case, and it's not seen, for example, in the charmed meson decay. So this is not seen, for example, in the CD case. There is a recent study by BESS3 which looked at the D plus decaying to omega mu plus nu mu versus D plus to omega E plus nu nu E, and the result is perfectly consistent with the standard model prediction, which is out of 1 here. So there is no such deviation coming in then the second generation. It's only in the third generation. So maybe nature is telling us the third generation is somewhat special. Okay. The other point I would like to mention here, since this is a tree level process in the standard model, so whatever new physics contribution you would have to explain this new physics, so the new particles must be relatively light. By relatively light, I mean should be below roughly TeV scale. You cannot have very heavy new particles to explain these anomalies, and that's very interesting because then you can probe it in the LHC, for instance. Okay, so now let me talk about the RK star anomaly. This is in the neutral current sector. So here, this is parameterized in terms of the ratio of the branching ratios B to K mu mu versus B to K EE. And this is a flavor changing neutral current. So this is loop suppressed in the standard model. So you can have contributions, for example, from these penguin type diagrams. So there have been different measurements of this by both LHCb and Bell. So here's a table from a recent paper which lists all these different measurements, and also the corresponding standard model predictions are there. So if you combine all of that, then you would get something like this. So this is the 1 sigma, 2 sigma, and 3 sigma experimental results, and this is the standard model prediction, which is sitting exactly at 1. And as Christoph mentioned, so the theory uncertainty in this case is very, very small. So, this is, yeah, it's kind of more robust. And now, to what kind of new physics would contribute to this? So you can write an effective Hamiltonian and look at the different operators. So here I've listed 4 different operators: this O9, O9 prime, O10, and O10 prime. And then if you look at the global fits to the data, then what you find is that it's mostly basically the C9 equal to minus C10 that gives the best fit to the data at the moment. And the pool with respect to the standard model is almost at the level of 6 sigma. This is from this recent paper after Morion this year. So here, since this is a loop-induced process in the standard model, so the new physics contribution here, the new physics can be heavy. It doesn't need to be exactly at TeV scale. It can be like multi-TeV scale. So that's one drawback, I would say, with respect to the RD star anomaly, where the new physics must be light. But nevertheless, you can still have TeV scale new particles explaining this anomaly, and this in principle could be accessible to the high Lumi LSC, for instance. Okay, so now let me just talk about some common new physics solution to all these different anomalies in all the different flavor anomalies, in particular the mu(g) -2, RD star, and RK star. So once you try to explain all 3 of them in the same framework, then the number of possibilities drastically reduces, and there are only very few, like a handful of choices now you have to explain all these 3 anomalies. A popular choice is, of course, lepton quarks, and in particular, a single scalar lepton quark could, in principle, explain all these 3 anomalies. This was pointed out in this nice paper by Bauer and Neubert. So the idea is that you can have the B2 C tau nu by this scalar lepton quark at the tree level, and then B2 S mu mu you can have through this loop again by the same lepton quark. And then the mu(g) -2 can also explain by having this phi in the loop, and also there's a top quark in the loop. So this is chiral enhanced. Okay. So this is a very nice solution. However, this is now disfavored by global fits, in particular, including the angular observables in the B2S mu mu, and also BS2 phi mu mu, and so on. So this is not really a viable solution anymore. And there's a nice scorecard from this paper which shows this. So this single scalar, there's S1. This can only explain RD, but it cannot explain really RK. You can have also other lepton quarks. So there are 2 other scalar lepton quarks that are considered here, the R2 and S3. So again, none of these could really explain both RD and RK. However, if you go to vector lepton quarks, then it turns out that this E1 vector lepton quark, it can, in principle, explain both RD and RK. But you have to be a bit careful about the vector lepton quark solutions, because you cannot just have a vector lepton quark without having a UV completion. Then the theory becomes inconsistent. So you must embed this into some UV complete model in order to make sense of the loop calculations in this case. And there have been some work in that direction, trying to have UV completion for the vector lepton quark. But I think more work is needed in that direction. The other possibility would be to invoke more than 1 scalar lepton quark. For instance, you can have a S1 lepton quark doing RD, and you can have a R2. You can have an S3 doing RK, or you can have R2 doing RD and S3 doing RK, for instance. So you can have you can have more than one to explain these anomalies. And there have been some works in that direction as well. So the good thing with this lepton quark is that, as I said, you can have chiral enhancement for the mu(g) -2. So because you have the top quark in the loop here, and then you can have this is enhanced by the top mass. The other interesting point here is that the same lepton quark, it can also give you new contribution to the Higgs to dilepton decays, because you have this this kind of coupling between the Higgs and the leptoquarks. And then again, if you have the top quark in the loop here, then you also get a new contribution to the Higgs to dilepton decay. And the ratio or the signal strength here, it depends it depends on this loop factor. So it depends on the leptoquark mass, and it also depends on the on this quartic coupling strength, which I call here, and this is in a particular model, our two leptoquark model. So this depends on this on these two parameters, the lambda and this lambda primes. Okay, but the point here is that if once you plug that in, then you find that in the parameter space that's allowed, so there's a negative correlation between the Higgs to mu mu versus Higgs to tau tau branching ratio. Okay, so in this case, the leptoquark solution to the mu g minus 2, it predicts that the Higgs to mu mu will be smaller than 1 in most part of the parameter space, and Higgs to tau tau will be larger than 1. And the percentage deviations here that can be seen, for example, in the high Lumi phase or in the future colliders like ILC or FCCHH. Okay, this is like a few percent level discrepancy you can find. Now for further details, you can look at this this parallel talk by Anil, who will discuss this in some details, I believe. Okay, so now let me talk about some complementary tests of these leptoquark solutions, yeah, not just leptoquark, any BSM solutions to these B anomalies in the high PT LHC. So the basic idea is
5 minutes left. Sorry, 5 minutes left.
Yeah, thank you. So the basic idea here is that whatever new physics operator you have to explain these B anomalies, B2C tau nu or B2S mu mu, these are the underlying processes, you also have the same new physics contributing at high scale. For example, you can have contributions to PP to dilepton or PP to tau nu. Okay, so if you have this new physics at this low scale contributing to the B anomalies, then you must see some effect in the high PT tails in the LHC. Okay, and this you can apply to both the the neutral current and the charge current. For example, if you have B2S mu mu, then you should see some effect in PP going to mu plus mu minus. And similarly, B2C tau nu will give you some effect in PP going to tau nu, or by C2 invariance, you can also see some effect in PP to tau plus tau minus. So there is one caveat though here, that the effective field theory is really valid at the low scale, because the B the B physics, the B decay is happening at 5 GeV 10 GeV scale, whereas if this new physics operator mass is smaller than the center of mass energy of the LHC, so then you cannot really apply this effective field theory there. However, you can then go to the simplified model approach, and then you can have this whatever blob here you have, you can resolve it and then have some simplified model. You can have some new particles there, for example, G prime or leptoquark. You can analyze that in those models, but the general argument still holds that you should see some effect in these high PT dileptons searches. And very recently, there was this CMS analysis doing just that. They looked at this the diimmune versus the dielectron differential cross sections, and then took the ratio and compared that with the theoretical prediction. And there seems to be a mild discrepancy at 1.8 TeV there. And so Tulika mentioned that in the plenary talk this morning. So if you want more details, you can look at her talk. So what would be the implications of these high PT-LHC searches for the particular BSM models? Well, here let me just take an example of this leptoquark model. So as I said, we need more than one leptoquark if you have scalar leptoquarks to explain both RD and RK anomalies. And so here we just take one example here, R2 to explain the RD star, and S3 to explain the RK star. So both are happening at the tree level here. But the point is that you can also produce these leptoquarks either in pairs or singly, or you can have this the non-resonant contribution through the T channel. And all of this would give you very stringent constraints on the leptoquark mass and the couplings. So from the pair production, you can already get a lot of constraints here on the branching ratio, depending, of course, on the branching ratio of this leptoquark decays to various standard model particles. But more importantly, from this non-resonant dilepton channel, from PP going to L plus L minus, you can already get stringent constraints on these Ikawa couplings of these leptoquarks. And in particular, you can see here, so if you look at this plot, so all these different channels, none of these couplings can be order 1 for a 1 TeV leptoquark, for instance, okay? So this is a very stringent constraint, and this has a lot of implications for the allowed parameter space to explain the B anomalies. For instance, this constraint, it kind of puts you into this very tiny part of this parameter space where you can only explain the RDRD star anomaly here. All the other parameter space is excluded. Okay. Another new physics solution you can have is in terms of R parity violating supersymmetry. So of course, I don't need to motivate this audience why supersymmetry is very interesting. It solves this gauge hierarchy problem very naturally. And but the one thing I want to point out here is that to solve the hierarchy problem, all you need is a light third generation fermion. Okay, so the first 2 generations can be heavy. So you can, in principle, decouple them from your low energy theory. So only take the 3rd generation. This is usually termed as natural SUSY. And then if you include R parity there, then you can, in principle, also explain both the RD and RK. Again, I don't have much time to explain all the details here, but here you can get a tree level contribution to RD and RD star, and either tree or loop level contribution to RK and RK star. So in this case, also you get very distinct collider signals. Again, looking at the operators, you find that so whatever the same operator that contributes B to C tau nu will also, by crossing symmetry, lead to PP going to B tau nu, for instance. So you can look at the PT distribution of this B, for instance, and then you would find that this is very different from the standard model background. And similarly, B going to SLL will lead you to PP going to BLL. And then for the right combination of the B and one of the leptons, you would get a peak of this quark in the distribution. So this should be very clear signature of this new physics contribution there. And you can also have other processes like T mu mu or T tau tau, for instance, and then you can have some sensitivity in the high Lumi phase and also in high energy colliders like 27 TeV or 100 TeV colliders, which in principle can probe all the parameter space that can explain this all these B anomalies. And the last thing I want to mention here is that the same RPP contribution can also lead you to very distinct signature in the multilepton channel, because if you have a contribution through this neutrino, for instance, because this neutrino is charged under the SU2, you can directly produce it through the Z, and then each neutrino now goes to 2 leptons through this RPP coupling, the same coupling that explains the mu G minus 2. And now you can have this very clean 4-lepton signature. And in fact, Atlas has done a very recent updated analysis on this 4-lepton channel. And if you recast that into this parameter space, then you find that now almost up to 700 GB neutrino is ruled out by this 4-lepton channel. And then there's only very tiny parameter space remaining to explain the mu G minus anomaly. And this should be completely accessible at the 14 TeV LHC. Okay, the last thing I want to mention, the connection to neutrino physics, the same new particle that explains the B anomalies and the mu G minus 2 can also contribute to the neutrino mass through the radiative corrections. And here are some examples in the case of leptoquarks and in case of RPV SUSY. In both cases, you get 1 loop contribution to neutrino mass. And we know that neutrino mass necessarily requires some new physics beyond the standard model. So this is one extra motivation to consider these new physics scenarios, because they can simultaneously explain neutrino mass as well. And in terms of new signatures in this sector, the same new particles will also contribute to neutrino non-standard interactions, and they would have some, in principle, observable effects in the future neutrino oscillation experiments, like D1, for instance. Okay, so maybe I'll just say one word about this. Looking far into the future, if the muon G-managed anomaly is really confirmed, then there will be a very strong motivation for a muon collider, because there is a very interesting recent work that shows that there is really no loose theorem for muon collider. Whatever new physics you have to explain the muon G-2, it cannot be very heavy, first of all, and then it must show up in this in a muon collision. For instance, looking at this Bhaber type scattering mu mu going to mu mu, or you can look at this the single production, the Drelian pair production, all that. And you can completely probe this whole part of the parameter space that explains the muon G-2, as well as RK star here. So I believe there is the parallel talk which will talk about some of this. Okay, so let me conclude here. Since I have run out of time, I'll just leave the conclusions out there. I'll just mention one thing, that that maybe these flavor anomalies, they are really the breadcrumbs, and they're leading us on the right path to new physics. So So just keep an eye on that. Thank you.
Thanks a lot for this comprehensive review of anomalous signal at LHE and elsewhere. So time for questions. So I can see one in the chat. For RD and RD star, instead of taking the ratio of taus to electron and muons, is it possible to take the ratio of muons to electrons as an additional test of lepton flavor universality? Do the experiment not differentiate between muons and electron in their analysis?
Okay, so I guess this is, yeah, this is a good question. Maybe some experimentalists in the audience can correct me if I'm wrong. So there, I think, yeah, let me go back to that slide. Just 1 second. Yeah, so the question here is that, so why can't we take mu1 E here, right? Well, so that will be close to 1 in the standard model. So here the difference between tau and the E and mu is mostly because of the phase space. And then you can also, you have also this different decay modes for the tau that you can look. So so maybe so experimentally they can probably also look at the E versus mu. I don't know if people have looked into that really. Yeah. So theoretically, I don't see anything that will prevent you from looking at that down as well.
Okay, thanks. So Kostu Bagashe would like also to know whether some of the RPV couplings that you are considering actually are similar to leptoquarks or not.
Right. Yes. So yeah, so if you look at the couplings here, so some of the couplings are of course order 1 here, similar to in the leptoquark scenario, and some other couplings. Yeah, since in the RPV case we have a lot of new couplings, so we have to just do some answers and just switch off most of the couplings and just keep the ones that are relevant. But they're of the, yeah, so you need some of the couplings to be order 1 and the mass scale here to be again in the multi-TeV range in order to explain the anomaly. So in some sense, the RPV is similar to the leptoquark. If you look at the LQ, if you look at the LQD type of interactions, but there is also another interaction, the LLE type interactions, that also becomes relevant in particular for the RK and also for the G-2, which is not there in the leptoquark. So in that sense, RPV is probably it provides more compared to what leptoquarks can do, I would say. And also it has a stronger motivation, of course, because it's coming from supersymmetry.
All right. Okay. Any other urgent question? We are already running late. Yeah, Jim Klein. Maybe you can turn on your microphone. You're probably muted, right? Okay, good. Mm-hmm.
Yes, you can hear me now.
Yeah.
I was just wondering, do you know if there's any prospects experimentally for corroborating some of these anomalies by changing the flavor of the spectator quark, i.e. B sub S decays?
Okay, again, that's a good question. Maybe for an experimentalist.
Yeah, I should have asked them, but.
Okay, so you're wondering, instead of U here, for example, you can just take a D or another spectator quark. Is that right?
Yeah.
So okay, so here I think there are yes. So people do look at the B. Okay, so for RK they look at the B plus to K plus L plus L minus, and for RK star they do the B naught to K naught L plus L minus, if I'm not mistaken. But you could also do the other ones. I think it's mostly experimentally, so you know how we can really find this particular final state, and yeah, this has to mostly do with the experimental things. But in principle, yes, you can do that. But as far as the new physics is concerned here, so this is all the action is happening in the other leg here. This is the B to S LL transition, so that should not change anything on the theory side, I believe. But again, right. So I would leave it to some experimentalists to comment on that.
Thank you.
Okay, thanks a lot. So any other urgent questions? Doesn't seem the case, so thanks a lot. And before, oh, yes, there is actually one. Okay, so Alexei Petrov comment that there are actually results for B sub S to phi L plus L minus.
Right. Yes. Yeah. So there are some results on that, though I think it's not as significant as these ones, and also there have been, I think, yes, the Bell 2 will have some new results. I think, as we heard just in Christoph's talk, that I think some of that could be improved in the future. Yes, that's right.
Okay, so let me thank Bhupal and